Good morning everyone. My name is Dr.A.Packia Antony Amalan, working as Associate Professor in Mechanical Engineering, PSM College of Engineering Technology, Tirunelveli. Today I am going to present some basics about CFD, that is abbreviation for Computational Fluid Dynamics. Computational fluid dynamics is the branch of fluid mechanics that uses numerical methods and algorithms to analyze and solve problems using fluid flow. In basics, the subject is mainly use the numerical methods. In mathematics, numerical approximation method is that is the main backbone of the subject. Numerical methods and algorithms to analyze the fluid flow. When fluid flow moves from one place to another place, so what are the properties change in the fluid flow? That is the main objective of this course. CFD convert the governing equations of fluid dynamics, that is mainly based upon Navier-Stokes equation, into discrete algebraic form that can be solved using the computers. It is basically the simulation of fluid flow, heat transfer, mass transfer and chemical reaction. So in this subject mainly use the discretization. We have to discretize the entire domain. So then we analyze the fluid properties. In this method, three different approaches are there. One is finite volume method, finite element method, another one is finite difference method. Finite volume is a control volume method. It is used in CFD. Finite element method mainly used in finite element analysis to analyze any structures. In the using stiffness matrix, we analyze the structure, slope, deflection, everything. In the first and third, the finite volume method and the finite difference method is mainly used in the computational fluid dynamics domain. These are some applications of CFD course. It is mainly used in the automotive industry. First, in the it is used in aerodynamic analysis of vehicles, aircraft winglet, everything. While moving the aircraft in the space, so how much the fluid property will vary. Then only according to them we predict the characterization of the fluid properties. Next, thermal management of engines and batteries, cabin comfort simulation, emission and combustion studies. These are the automotive industries. Another one is separate aerospace industry. In the aerospace industry, to analyze the aircraft wing design and optimization, we use the CFD. And to analyze the jet engine combustion and cooling, we use the CFD software. Then to analyze the supersonic and hypersonic flow analysis, we use CFD. Next, in spacecraft re-entry simulation, also we use the CFD software. Next, it is applicable in mechanical and processing engineering. In the design of heat exchanger and turbines, pumps. The heat exchanger turbine pumps are blades are there. So while rotating the blade, how much the fluid property will vary from inlet to outlet. Also we can use this software CFD. Another one, HVAC. We know that heating, ventilation and air conditioning system. It is used in home also. Optimization and mixing of chemical reactors, flow through pipes and ducts. In smart home building also we use the HVAC design. It is based upon the CFD software. Next, in the biomedical application, the fluid blood flow. Every human blood flow analysis also possible to analyze using the computational fluid dynamics. Then airflow in lungs and nasal cavities. Next, design of medical devices like stents and inhalers also use the concept of computational fluid dynamics. Next application is energy sector. In wind turbine performance analysis, we use this concept technology. Then combustion in thermal power plant. Next, cooling of nuclear reactors, solar panel heat transfer analysis. In this area also we use the CFD technology. Next, in environmental and civil engineering also we use the CFD to predict or control the pollution dispersion in air and water, weather, climate modeling, flood and drainage system simulation, river and coastal hydraulics. Next, architecture building design also we use the CFD. Wind loading on building, smoke and fire propagation, indoor airflow and thermal comfort studies. So from the these points we come to know that so in almost every domain of engineering field, whether it's a civil engineering or mechanical engineering or marine engineering or chemical engineering or mechanical engineering, every engineering use the CFD application, mainly for aerospace and mechanical, biomedical, every engineering. To analyze the simulation before going to the real product, we have to simulate what is the real performance using the computational software. So it is very useful and very much applications in the for the engineering students. So these are the steps involved in the CFD analysis. First one is geometric modeling. We have to model to analyze the parameter. For example, to analyze a aircraft wing means we have to model that cross section of the wing. Then you go for meshing. So these and all we have discussed in this PPT also. So there are so much different types of meshing is there. So meshing is one of the most important. So because how much mesh accuracy and error reducing means only we have to get the good result. Then physics definition, that is a boundary condition. We have to apply the boundary condition. What is the inlet parameter? What is the outlet parameter? What are the basic equations followed to predict the flow? Then solving, it is based upon the it is run in the using computers. It may so much iterations of that to convert the so many equations. Then post processing. So post processing we simulate the fluid flow in velocity contour or plus pressure contour or density contour. So in that so we have to easily visualize whether how much pressure inside the inlet condition. So this pressure how much vary, whether it is a reduce or increase or constant. So then according to the geometry property, according to the mechanical property, so we have to analyze whether the system is capable or not. So how much stress and strain will be induced in this material. So then we can decide whether we go for this same model or we have to do some modifications. That is we can easily predict using this software. So it is very interesting and most emerging field in the engineering field. So in the right side we use different steps simulation, mainly using the software ANSYS everyone know that. Then in geometry also you can simple drawing means you can model in ANSYS itself. Otherwise so many modeling softwares are there. So from that software you have to model, then import into the software. Then mesh, ICEM, ANSYS meshing, tribograd, these are different types and methods to mesh the geometry and boundary control volume. Then simulation, CFX, fluent, body flow, FENSA, YC, these are included in the ANSYS software itself. We can simulate the fluid flow according to the equations. Then analysis and post processor. So in this video we discuss some basics in this steps involved in the CFD. This is the modeling overview. This is in pre-processing, solver and post-processing is there. So pre-processing, solid modeler, next mesh generator. Then solver setting, these are the solver settings. In the solver setting there are equations, many equations are there. So this fluid dynamics analysis cannot be performed manually because these so many equations are have to iterate more than 100, 200,000 times to converge all this equation. So that using computer only we can analyze this fluid properties, that is called computational fluid dynamics. The transport equation is mass, conservation of mass, conservation of momentum, conservation of energy. Three major equations are there: conservation of mass, conservation of momentum, conservation of energy. This is a basic equation. Next equation of state. Then supporting physical models. Supporting physical model means the physical material property, what are the boundary conditions, what are the initial conditions. Material property means the whether the material is isotropic nature or orthotropic nature. What is the Poisson ratio, what is the Young's modulus of this material. Then what is the boundary condition. What is the boundary condition means condition at boundary. After we plot the control volume domain. So what is the inlet condition, what is the pressure, density, temperature. Then what is the outlet condition, pressure, temperature, density, these are the boundary condition. So we have to feed this known input boundary condition to the solver equation. Then the system will analyze or iterate in many number of times. So it will predict the required output. So the initial condition also we have to initialize with this initial condition. What are the initial pressure, initial temperature, initial volume, initial temperature. Then based on the equation, what the output temperature, output pressure, output condition we have to predict. These are some physical models are there: turbulence model, combustion model, radiation model, multi-phase, phase change, moving zone, and moving vessel. These are the different physical model available in the CFD. Then after processing, after iterations are done, all the equations getting converged to some same values. Then post processing we can visualize the CFD flow after the post processing process. So while starting the CFD analysis, we have to very much strong about the mathematical fundamentals. So for that, it is very essential to know from the partial differential equation. So in mathematics we studied the exact differential equation, that is dy by dx. So but is in numerical methods we can approximate the exact differential into partial differential equation. It is represented as dou u by dou x. So there is a partial differential equation. The general form of the partial differential equation is a, there is a constant value, a, b, c, d, e, f, g are constant value. So first dou squared u by dou x squared, b dou squared u by dou x dou y, plus c dou squared u by dou y squared, plus d dou u by dou x, plus e dou u by dou y, plus f of some function, then constant equal to 0. So once again I repeat, because it is a very important in the CFD knowledge. So a dou squared u by dou x squared, that is a dou squared u by dou x squared is a second order partial differential equation in the direction of x. The coefficient is a. Then another second order differential in both directions, x direction as well as y direction, the coefficient is b. Then the second order differential equation in the y direction, that is a dou squared u by dou y squared, the coefficient is c. Then another is first order differential equation, dou u by dou x. Another first order differential in y direction, dou u by dou y. Then function some constant equal to 0. Therefore we have to summarize the x squared direction, the second order x squared direction coefficient is a. The second order x and y direction b. Second order y direction is c. So if we calculate the b squared minus 4ac, that is a coefficient of xy term, that is a b. So b squared minus 4ac, a what is that? That is the coefficient of dou squared u by dou x squared, and c what is that? So dou squared u by dou y squared. So what is the coefficient value of the equation? Any equation, for example Laplace equation, Poisson equation, or heat flow equation, any equation. So we have to first write in terms of general PDE. So we have to find what is the a value, what is the b value, what is the c value. So from that value we can conclude the flow is belongs to which type of flow. That is because there are basically three types of flows there: elliptic, parabolic, and hyperbolic. So here some geometries are there. So how the flow will come into the elliptical flow. So if we cut the cone in the particular angle, so we get the elliptical curve. So the flow property follow the curve nature. Elliptical nature means that flow is elliptical flow. If we to get the parabolic nature, so see the second third diagram. So it is cut the parabola cube like that. So the arc, it is mentioned in the red color. So the flow is come like this direction, like this nature, that is called parabolic. So hyperbolic, so when we cut the same geometry in the plane like this, so we get the two rectangular, that is first one upper side, the next one. So this is called the hyperbolic flow. So see, first one is a in red color, it is mentioned in elliptical type, that is a parabolic type and hyperbolic type. So three different natures of fluid flow. So it can be calculated with the simple equation b squared minus 4ac. So whether we get the value, what is the value of b squared minus 4ac is negative or less than 0, the flow is elliptical. If the flow is elliptical, what is the condition? B squared minus 4ac less than or equal to 0. That is meaning negative value. So parabolic, so B squared minus 4ac equal to 0. When we substitute the coefficient BAC, that is a B squared minus 4ac equal to 0 means the flow follow the parabolic nature. So similarly, if we calculate the B squared minus 4ac is positive value or greater than 0, it means positive value. So that type of flow follow the hyperbolic nature. So from the given second order PDE equation itself, we can find the type of flow, whether it is a elliptical or parabolic or hyperbolic. So the audience can easily understand. If we get the value minus means the flow will follow the elliptic nature. So if we get the equal to 0, the flow will get the parabolic nature. Then if we follow the hyperbolic nature, so the flow follow the hyperbolic nature, B squared minus 4ac greater than 0. So some example we can discuss here in this platform. So everyone know the Laplace equation. Laplace equation means dou squared phi by dou x squared plus dou squared phi by dou y squared. It is also mentioned as dou squared del squared phi equal to 0. So this is everyone know the equation, that is a Laplace equation. So how we find the Laplace equation belongs to the elliptic equation? So in previous slide we know that the coefficient of A, B, C, that three coefficients we have to find. So please remember, A is a coefficient of x squared term, B is a coefficient of xy term, C is a coefficient of y squared term. See the equation. So here x squared, second order x squared coefficient is A. So here A is 1. So A equal to 1. Then similarly dou squared by dou y squared, that is a coefficient of C, because the dou squared by dou y squared, the coefficient is C. So therefore A and C are 1. But in this equation there is no terms of x and y, the second order dou squared by dou x dou y, that is a coefficient B. So here the term is not available. So therefore the B term value equal to 0. So substitute the value B squared minus 4ac 0 minus 4 A 1 C 1. So 1 into 1 1 minus 4, so minus 4. So here 0. Therefore the result is minus 4. Minus 4 is defaultly less than 0. So therefore the equation is elliptical equation. Like that we have to predict from the given equation what is the type of flow. That is very important. So this is one of the best example. Similarly the Poisson equation also same measure, but having function. In that function there is no B, A, C, that did not come into the value. Whether it is 0 or some function, it is the same value, because there is no B term, there is a 0. There is a term, dou squared by dou x squared 1, dou squared by dou y squared C term 1. So therefore defaultly negative value only obtained for the both Laplace equation and Poisson equation. Therefore these equations follow the elliptical flow nature. So what is the applications? Steady state heat conduction and electrostatics incompressible potential flow follow the elliptical nature. So then next we come to the second type equation, parabolic equation. So it is already we told B squared minus 4ac equal to 0. So while substitute this value equal to 0 means the type of flow is parabolic nature. So here for the example is unsteady heat conduction equation. So what is the unsteady heat conduction equation? Dou phi by dou t and alpha into dou squared phi by dou phi. So this is the equation format. So we can write in that format also. Dou phi by dou t equal to alpha into the dou squared phi. We write dou squared phi by dou x squared plus dou squared phi by dou y squared. So here also we see this is a first order term dou u by dou y. So this is a dou squared by dou x squared, that is a term. This is a C term, dou squared by dou y squared. There is no B term is there. Therefore while substituting, so we get 0 value. 4 into minus that is if we convert into this side it will come negative. So therefore B squared minus 4ac equal to 0. Therefore, the heat equation also follow the parabolic nature. So, what is the applications? Transient heat conduction, diffusion problem, viscosity and unsteady flows, we follow the parabolic nature. So, third type of equation, hyperbolic equation. So, if we find dou squared u by dou t squared is similar to dou y squared. So, this is a constant term of A. So, A equal to some c squared equal to 1. Therefore, A equal to 1, c equal to minus 1. Therefore, minus 4 into minus 1 plus 4. B term not available. Therefore, the total value becomes a positive. Therefore, the type of flow is hyperbolic nature. So, see, this is the three graphs, that is a elliptical nature, this is a parabolic nature. If you rotate into the we get parabolic shape. This is the hyperbolic shape. So, what are the applications? It is applied in the sound waves, shock waves and CFD and vibration and structural waves. We use this type of hyperbolic flow will be happened. So, next important we have to come with the grid method. So, in that grid method we have to divide the each grid, that is if you imagine this is a control volume of a particular object. So, this is the inlet condition, that is a outlet condition. You say the x value, in the x direction every nodes are mentioned as a I value. So, for instance you take the center node, that is I comma j. What represent it? I represent the horizontal direction, j represents the vertical direction in the y direction. So, initially we see the center node, that is I comma j term. So, see, if the next increment from the I comma j node, the each intersection, it is shown in the circular point, that is called the node. So, the right side increment, so we get I plus 1 term. So, I plus 1 comma j, that is the right one side. If we go over the previous node, what is the previous node representation? I minus 1 comma j. So, I minus 1, there is no y axis variation, therefore j, all three nodes j only there. So, I minus 1 comma j, I plus 1 comma j. Similarly, in the upward direction, if we go the vertical direction increment, what is the representation? I comma j plus 1, because in the x direction there is no increment. Therefore, I, in y direction one increment, the j plus 1. So, I plus 1 comma j minus 1, j plus 1. Similarly, the downward direction there is no I direction increment, but j direction increment. Therefore, I comma j minus 1. Similarly, the top corner, see the top corner position, there is a both increment in the positive direction. Therefore, I plus 1 comma j plus 1. Horizontal direction 1 unit increment and vertical direction 1 unit increment. Similarly, the downward direction, horizontal direction 1 unit increment I plus 1, but vertically downward. Therefore, j minus 1. See this node, what is the position? I minus 1 comma j plus 1, because it is given the x direction 1 unit minus and y direction 1 unit increment, there is a j plus 1, I minus 1 comma j plus 1. So, this node in x direction 1 unit decrement and y direction also 1 unit decrement, therefore j minus 1. See, remember, once again I repeat in fast. So, the central node I comma j, the right node I plus 1 comma j, left side I minus 1 comma j, top node I comma j plus 1, top bottom node I comma j minus 1, the corner nodes I plus 1 j plus 1, I plus 1 j minus 1, I minus 1 j plus 1, I minus 1 j minus 1. So, these are the 9 adjacent node to the I comma j node. So, these are the representation. So, each node increment del x, the del x is 1 unit. So, here vertical direction del y is 1 unit. So, from that value, so we predict the partial differential equation. So, in previous previous slides we discussed about partial differential equation. So, from the partial differential equation, how we find the values using the grid method. So, this is the most important in the CFD section. To get the value of partial differential equation, that is a first order PDE or second order PDE, we can determine the value from the grid value. It is based upon three different approaches, that is a forward difference, that is a backward difference and a central difference. So, forward difference, what is the formula? See the formula, the x direction increment, that is a f or u of I plus 1. So, what is in both way we can represent. the xy x direction increment minus the corresponding node f of x comma 0 by h. So this is a forward difference formula. See this slide, it is can be useful. Dou u by dou x, the forward difference is u of I plus 1 comma j minus u of I comma j divided by del x. So that is a forward difference. In y direction means, so u of j plus 1 minus u of I comma j divided by del y. That is a y direction. That is a forward difference. Backward difference means from the central node, what is the difference to the backward. So u of x, f of x comma x naught, that is I comma j term, minus of negative direction f of x naught minus h. What is the distance? What is the difference? Divided by the h. If we in the x direction del x, if we y in the del y, that is a first order differential equation in the forward direction. That is a forward difference method or backward difference method. Once again I repeat, in the forward difference, if you take the I comma j node is a center. So what is the next increment? I plus 1 comma j. So we subtract the distance between the I comma j1 to comma j to I comma j. So what is the difference here? So this difference minus u of I comma j divided by del x means dou u by dou y. Dou u by dou x. So to determine the partial differential equation using the grid method, this is a formula. If you go for backward difference, this is the I comma j value. So the backward value I minus 1 comma j. So subtract these values, u of I comma j minus u of I minus 1 comma j. Otherwise it is represented as f of x comma x naught minus f of x naught minus h. So this distance. So this distance divided by x means that is a dou u by dou x. In y direction means dou u by dou y in the backward difference approach. So if you approach the central difference means you take the node is a center. So what is the center difference? You consider the positive direction as well as negative direction. So positive direction is I plus 1 comma j, negative direction I minus 1 comma j. So what is the distance? You got to subtract I plus 1 comma j to I minus 1 comma j. Both the distance we got to subtract. Then divided by this 1 unit del x, this 1 unit del x. Therefore 2 into h. So in the previous step we find the h. We use h term. Here 2h. Why 2h came? So here 2 units. So we consider the 1 increment of positive direction, 1 increment of negative direction. So therefore this is the 1 unit h, this 1 unit h, therefore 2h. If it is mentioned in the x direction, that is a dou by dou x, y direction dou by dou y. So using the central difference method, this is the 3 approaches to determine the partial differential equation using the grid method. Understand? Okay. So why we go for this forward difference or backward difference or central difference means, so in the flow, if it is follow the it is flow like a curve. Every flow there is a not follow the straight line or linear line. So everyone having flow in the curve linear direction only. So to analyze the properties, so it is very difficult to predict the every single point, intermediate point in the curve. So therefore we use these 3 nodes. See this diagram. So this is a one node, this is a one node, this is a one node. That is a I plus 1 increment node. This is I comma j node. This is I minus 1 comma j node. So to predict the curve value, that is a exact 100% accuracy value. But in there is a approximation method. So if we use the forward difference, so we find the increment term u of I plus 1 comma j minus u of I comma j. This is a forward difference portion. So see this straight line. So if we use this value forward difference approach, we calculate the flow parameters using the straight line method. So if we follow the backward difference, see this equation u of I comma j minus I minus 1 comma j del x. So this inclined line represented as a backward difference method. So in order to predict the curve properties, we use the forward difference or backward difference. So this line represents a central difference. Central difference consider the forward direction point as well as negative direction point. So this is a central difference method, u of I plus 1 minus u of I minus 1 by 2 del x. The already previous slide we discussed. So from the approximation, we approximately predict the flow properties in the curvilinear path. So for that only we use this approximation approach, forward difference and backward difference and central approach. So in this second diagram, it is almost clearly it is mentioned. If we follow the exact curve like this, so to approximate, we calculate the straight line. There is a forward difference or backward difference or central difference. We approximately find the value. So how much exact value will come, how much error will come when we follow the distance more, so the error will come. So if we discretize into small node, so the del x distance is very less means, so we get accurately closely to the curve because you see the graph, it is easily visible. Okay, so when we go the how much possible we reduce the del x distance, so we get the accurate curve properties. So this is the aim. So next in the grid, so this type of grid while analyzing the CFD, there are so many different types of grid we followed in the control volume. So first type is Cartesian grid, that is a quadratic or arc tree, then structured grid and unstructured grid and hybrid grid. So these are the different types of grid. So monoblock and multi-block, these are the different types, subdivisions in the structural grid and unstructural grid, tetrahedron and quadrilateral and hybrid grid, both the structural and as well as unstructural grid. So these are the first type, Cartesian grid. It is in CFD. It is a structured grid where the mesh line are aligned. That is the important point. The mesh line is aligned with the Cartesian coordinate, that is x, y direction. It is aligned. So that is called the Cartesian grid. The cells grid are typically rectangular 2D or cuboid 3D. The grid points are spaced at regular or variable interval. So see the diagram. So this is a Cartesian type of grid for curvilinear surface, for linear surface. So these are the unstructured or and structured type. Structured grid connectivity between the grid points follow regular orderly patterns. So you note down the points, regular and orderly pattern. The curve means that is called structured grid. You see the unstructured grid. So this is doesn't follow the regular or orderly pattern. So the structured grid characteristics are grid lines are aligned in a structure or grid-like fashion. Cell connectivity is implicit and easily defined, typically used in the 2D and hexagonal 3D coordinate, commonly coordinate system, Cartesian and curvilinear coordinate systems. This is an unstructured grid. It consists of cell arranged in no regular pattern. In the previous we see the regular pattern. So here unstructured grid, that is a no regular pattern. Connectivity between grid points must be explicitly stored. So the connectivity stored, it takes more memory or more complex nature because it is mentioned it is highly flexible for modeling complex geometries. So main character is 2D arbitrary shape, 2D element 3D tetrahedron and connectivity stored in loop tables and great geometric adaptability if you go for the unstructured grid. Hybrid grid, structured and unstructured, it combines structured and unstructured grid. Example, near wall. For example, for the near wall times, it follows one type of grid, that is a structured grid. Around the complex region, when we go for the complex region, we are unable to follow the structure, therefore we use the unstructured grid. So that type of combination, we mesh will be followed. This mesh is called hybrid mesh. So understand, in the near walls or in regular pattern, we use some type of mesh, that is a structural region. If we in the complex feature, we use unstructured grid. So combined of both the structural and unstructured grid, use the hybrid mesh. So it is used in the hexagon, tetrahedron, prism and pyramids. So these are some examples taken from the publications. So it is the nozzle. So once we from the second order equation, we can predict the second order value using the grid. So we give input to the system. So what type of the equation, energy equations implemented in the fluid flow. So after so many iterations, 100 or 200 or 500, we can send into the simulation. So after run, so this is a post-processor image. So this is a post-processor. We can predict the fluid properties such as here velocity meter by second it is mentioned. So where it is the maximum value, where it is the minimum value, which region getting the dangerous situation, that is the maximum value occur, which is getting the lowest value occur, what is the profile, what is the domain, we can calculate using this CFD simulation. That is a beauty of this technology. So instead of before going to the real analysis using the practical components itself, we can analyze in the CFD computer itself. So once the value will be satisfied, so the obtained values is not satisfied means we can repeat the experiment from the beginning. So we can change the geometric properties or boundary conditions, inlet property, exit property. So what is the simulation will varied. So which property we can get the exact desired properties, we can go for that for further manufacturing or testing. This is one example for the aerofoil section flow analysis. So here the velocity contour, the static pressure contour it is mentioned. So what is the pressure? Positive maximum pressure occurred in the nose portion, so the lowest pressure occur in the upper side of the wing, and what is another yellow region occur in the downward side or front side. So from that figure we can predict whether the aerofoil will travel in the air. So any drag, how much drag will occur, how much lift will occur, how much the lift coefficient, drag coefficient, we can calculate from this value. So it is used in the aerofoil design. So it is very much helpful to predict the aerodynamic analysis. So these are another some examples. In the total aircraft also we can using this software we can predict if we in the flow path one circular duct available means how the flow it covers the object geometry. So behind the geometry what is the how much weight, how much the fluid rotation will be taken, and how much what is the pressure value, what is the value velocity value we can predict. So this is the space shuttle. So if we space shuttle, human travel inside the space shuttle while it travel from the atmosphere to earth. So how much the pressure density will vary while traveling, huge velocity, huge temperature, and huge abnormal atmospheric condition. We can predict the property in every real product, because to manufacture each component itself it takes huge amount of money. So each and every time we can predict, we can analyze we can test in the real prototype. So therefore we go for this technology, that is CFD. Thank you. From this I conclude my brief introduction about the CFD subject. So I advise everyone, engineering students, that is initially we discussed in all domain of engineering field they using this CFD terminology, whether it is a mechanical, chemical or civil or biomedical or everything. We in marine also we can use the CFD technology. So everyone getting few points I summarize from that basic. So it is from the second order PDE equation we have to generate the type of flow. Then grid method we find the values, then approximate the energy equation, what are the equations used in the CFD, and we can iterate, then we can simulate. So after the simulation we can interpret the result, whether the result is applicable or useful, we can go for, or not, it is not suitable, or we can edit means we can edit. Okay, thank you. From this I conclude this presentation. We can see you later. Thank you.